I'm smiling. Yep, I'm smiling right now because I get to do probably one of my favorite reactions. So I'm extra excited. I hope you like it too. Sometimes that makes students groan when they know it's going to be my favorite. I hope it's your favorite. The Robinson annulation. So good old Robinson. Robinson actually played a big role in a lot of other parts of chemistry. He's a British scientist that won the Nobel Prize for this reaction. And it was a Sir, he was knighted for that as well. And Sir Robinson also, if you think about the way the reaction's named, annulation, you might have used the word annular or annulus in calculus. It's Latin for ring, right? So you're forming a ring. So it's annulation, means the ring forming reactions. So now you kind of know why it's one of my favorites. If you know anything about me, that I like forming rings. It's challenging and fun. So we're forming a ring, and we're going to be putting everything together. It's a big culminating reaction for this section. So let's do this. Let's jump in. So it combines Mr. Michael addition. It puts it all together. An aldol reaction. So we do an aldol addition, but we also follow it up with the dehydration. So it's important to remember those 3 steps in order to get the full mechanism complete. Here's the general picture. So we need an alpha beta unsaturated carbonyl, right? And then we need something that's going to be our enolate to attack it. So notice that's why the H's are drawn in. So the H's that are not drawn could have R groups instead, but we need at least these 3 H's, and then we could have R groups everywhere else. So we could have lots of other R groups, we could have other rings, we could have many other substituents. This is the bare bones right here. The bolded lines are preserved. So in other words, the non-bolded are the new groups. I'm going to highlight them just so we can kind of see new bond, new bond. Okay, so that's how we form the ring right there. We had to form 2 new bonds. New sigma bond, got a new pi bond. If we just think about this for a minute, and there's our dehydration, lost the water. All right, we have our mandatory H's. Let's just look at those. So what's their role? This is actually our first enolate. We're going to see this in the mechanism. It's going to attack that's what has to happen, right, to do a Michael. Attack the beta carbon of the alpha beta unsaturated carbonyl. There's our Michael. Once our Michael's kind of worked out, we got to do an aldol. So how do we do an aldol? We have to have another enolate. That's where the other hydrogens come in. Second enolate. But then we do a dehydration. So then we have to lose an H there. So because we do a dehydration, we lose the oxygen, right? So we're going to lose this oxygen. And we're also going to lose this pi bond. Notice how it's not there anymore because we did the Michael addition. So just a few things to kind of keep in mind how we track it, because it's going to be hard to just say, let's draw that new product without going through the mechanism. But by the end of this, I hope you'll be able to, because we're going to use the mechanism to help us set up a little template, a little pattern. All right, so I refuse to call it a trick. It's not a trick, but it's a pattern you'll be able to get derived from the mechanism. All right, so case in point, let's draw the product of this. This has all those key features, right? Here's our alpha beta unsaturated carbonyl, and here's a beautiful enolate waiting to happen. Resonance stabilized, really good for a Michael addition, right? So clearly that's going to be our thermodynamic enolate. But would you be able to look at that and say, okay, I'm going to form a ring, and I know I already have a ring, but I'm going to get another ring, and I'm going to make this fused ring system, and it looks like this. Right? That's challenging. Let's do the mechanism. Let's prove how this works first. And our mechanism should have those 3 parts: Michael, aldol, dehydration. So here we go. You got to be ready to sit down and really watch this on regular speed. Start writing. This is one to pay close attention to. Okay, so here we go. I'm going to go for the first enolate. Like I said, this makes the beautiful enolate. We have to do the Michael, right? So we have to attack that alpha, beta, and saturated carbonyl. So in order to do that, we've got to make our enolate. I'm gonna, like I said, I like to toggle between making the carbanion there or actually making a true enolate. So it's a equilibrium really, but I'll draw, we're trying to push forward, so I'll draw it this way. Okay, and then here's our Michael. And I'm doing that to emphasize that we have this resonance, right? So we push that down and then it attacks again. It's just like having the anion on the carbon. Okay, so we're ready to do the Michael. Attack that beta carbon. What does it do? Pi bond goes there, open up to there. We just made our first new bond. So here's our Michael step, M-I-C-H-A-E-L. All right, so now we did our Michael step. Let's draw our Michael adduct. That is all intact. Our carbonyl came back. So where is everything? It's on that middle carbon, right? New bond right here. Now I need to make sure I have all my carbons. I have 1, 2, 3, right? Before I get to my carbonyl. So I need a 1, 2, 3, and 3 is my carbonyl carbon. And that one opened up because I made an enolate there. Okay, so we're going to neutralize that Michael because we're going to wrap up the Michael so we can do the next part. So yes, this has a lone pair and it's getting a little small there. I'll zoom in for you. This is a little different than what I did in the last Michael where I mechanism, and you might want to do that side by side. First time I did the Michael mechanism for you, I went ahead and closed the carbonyl pi bond down and let the pi electrons land on the carbon and then neutralize that. This is just to go to show these are both perfectly acceptable, because what I'm going to do now is make the enol when I neutralize. If I neutralize first, I get an enol. And we know what to do with enols. Hope you're all saying it out loud. I think I hear you. Pretend I hear you. Tautomerize. Okay, so let's make our tautomer, keto. Okay, that is the Michael product. And if this was not the substrate that it is, we would be done. But it has the components necessary to allow it to keep reacting. So we're not done. What are those components? Those other hydrogens. Okay, so that means we get to form another enolate. Now it gets confusing. Where do I get the other enolate from? Well, I'm going to try to start simple and try to explain this product, right? And I'm kind of getting there. So see how I'm starting to match this? Like this part's resembling it. And I see I got to close the ring this way. Okay, so what that means is that this is going to be gone. It's going to be part of the pi bond here. So in order for that to happen, I've got to have this alpha carbon attack there. So let's make that happen. That is our second. That's our new step. That's the aldol step. So I'm going to throw in the hydroxide, and I'm going to label this. This is our second enolate formation. So now we're at stage 2 of Robinson. Okay, let me draw on the hydrogen I'm taking off. It is one of the green ones. It is required. All right, so I'm going to put that here and push it through. Okay, so I have that. There's my enolate. Right down here, I have my other carbonyl. Okay, so let's attack. Close. And let me make sure I have the right number of carbons. This is where I would attack from. 1, 2, 3, 4, 5, 6. Wonderful. We want to form 6-membered rings. That's what Robinson annulation does. This is the annulation step, the ring forming step. Close, kick the pi bond over to here to attack. Open up there. Oops, I was going to try to stay with black. There we go. Now, I need to make a fused 6-membered ring, fused at the 5 and 6 carbon. So I'm going to draw a hexagon now. Then I'm going to number carbons, because that's extra important now. 6, 5, 4, 3, 2, 1. Now I'm going to make sure I don't miss anything that was attached. Okay, so 5 is good, 4 is good, 3 is good, 2. Reform the carbonyl. 1 has a methyl. 1 also made the new bond to 6, so I'm good. 6 had an oxygen double bond, now it has an oxygen single bond, it opened up to an O-. Now we're very good. Okay, so this was an intramolecular aldol. That's the ring forming step. Let's neutralize that. Easy step, right? Good little brain break for you. Okay, so the fused carbons are going to now have an OH on one side and a methyl on the other. And then we still have a methyl at 1 carbon away from the OH. And then right there we have a carbonyl. Good. All right, so we've done 2 of the 3 stages. Michael, aldol. We need to do dehydration. That's easy. We find the alcohol. We find out which H needs to go with it to make it from OH to H2O, such that we will get an alpha beta unsaturated carbonyl. That conjugation is important. In other words, look at how close we are to home free. So I know this is kind of a weird type of elimination, but it's technically called the E1CB. So we're going to, but we've done it before, right? So we can see dehydration happen with OH as a leaving group, and we'll have minus H2O. So I'm not going to draw that out because this mechanism is long enough. So refer to the previous lectures to work that out. So right here is where we lose this H here to form this pi bond. So can you repeat that? Even more importantly, what if I said, okay, how about, we're going to do a retro of this. We're going to do a couple retros and forwards. But what if I said, what if I even just take this one? We'll come back to this one. We'll do some retros and then we'll come back. I think that'll be more rewarding because this one is hard enough. It has 2 rings fused. So we'll work our way up to it. Okay, so once again, Michael, intramolecular aldol, dehydration. Okay, so what you want to be able to do is probably not have to fill an entire page with a mechanism to do it every single time, although it's always good to double check. If you push for time, then you might want to practice this enough that you can start to see some patterns emerge, and that's our goal right now. Also, if you were asked what was the starting material that allowed you to get this Robinson product. So let's say you're told this formed from a Robinson. How did a Robinson form this? Let's think about the 3 steps. First, we did Michael. So we were trying to find what these are. Second, we did intramolecular aldol. Third, we did a dehydration. So if we're thinking backwards, we're going to say, okay, what was it like before we did the dehydration? That means before we did the elimination step, we had an alcohol somewhere. And if we label our carbons, and I'm going to zoom in a bit, alpha and beta, for the alpha, beta, and saturated carbonyl, the beta carbon is the one that used to have the OH. And we eliminated toward that alpha carbon to ensure that it would be the alpha, beta, and saturated carbonyl that was conjugated. Okay, so that takes care of one step backward. We got to get all the way back to where we have 2 separate pieces though. So this is one surefire way to kind of get there, is discretely break it up into 3 parts in order to work your way toward it. So now how do we do that intramolecular aldol? Oh boy, so if we did an intramolecular aldol, it means that OH was not an OH, it was a carbonyl, and it got attacked, and that's our aldol addition product. So let's get to that point. What do we attack it with? Of course, our alpha carbon. That used to be our enolate. So that's where we separate that, right there. So aldols are kind of, hopefully, familiar friends by now. And then Michaels, like I said, you want to be comfortable with them because that's getting us back to home base. Okay, so home base, to do the Michael, then we must have had an alpha, beta, unsaturated carbonyl once again. And that's on the other side of where the old one used to be. So it was over here. So if it was over here, that means the new bond was made here. This was our enolate. I'm going to put a little squiggly line there. In other words, let's see if this pans out. Alpha, beta, unsaturated carbonyl, ketone in this case, plus that guy to be our enolate. Yep, that would work. So how would we do that even? Can we like put this together to make sort of a little pattern here? Why, hello, Michael donor. Yes, I'm looking at you, thermodynamic enolate. And hello, Michael acceptor, alpha, beta, unsaturated carbonyl. You're the first step of Robinson. So I'm going to rearrange you to be in the right proximity. In other words, that's what I did. Now, we know the new bond is going to come here and result from there. I'm going to go ahead and start numbering. Carbons, 1, 2, 3, 4, 5. 5 will ultimately attack carbon 6, which is the one next to carbon 1, to make our aldol. because notice how carbon 5 can also be deprotonated to form an enolate. The enolate will attack here. So there's step 2 of Robinson, our aldol. The aldol attacks carbon 6, opens up that oxygen to an OH. The OH ultimately gets lost in an E1CB mechanism with as OH with a bad leaving group, but ultimately we also lose the H. So we can think of losing water altogether, even though it's not all in one step. So these two H's are ultimately gone. A nice way to remember that, even though that doesn't happen in one step in the mechanism, but there is a consequence of the entire mechanism, is that we lose water here. So, but we do get a pi bond as a result, so dehydration. Put it all together, everything from the original substrate stays intact in terms of the skeletal structure. One still has a methyl. We have a new 6-membered ring thanks to Robinson. And I'll number my carbons 2, 3, 4, 5. 5's a new bond to 6. And I'm going to color code them with the steps that I did. That the red sigma bond, the new pi bond from dehydration, and green was a new bond between 1 and 2 from the Michael attack. 4 kept its carbonyl, and we are done. There is a Robinson annulation in less than 2 minutes. Okay, now that the 2-minute marker has been made, let's take this a little slower. You want to remember, just to revisit, the 3 steps. Yes, I know you've been mad. This is not a easy mechanism, but once you get the hang of it, that acronym will not make you so mad. So take, what does the acronym mean? Michael, which I've color-coded in green. Aldols next, and dehydration last. So as long as you know that you're about to get mad with the Robinson, you've got to take your starting material and line them up so that you have it ready to do the first step, Michael. So you got to put the beta next to the happy enolate. Naturally, what will happen is the other side will be the second enolate, and it should be in a close enough proximity if you drew that this way to make that dotted line to the carbonyl that's connected to the happy enolate, because that's the aldol attack. Open and lose, ultimately this is OH, which is dehydration. Okay, I hope that helps you. Go forth and solve lots of problems.